Welcome to another Explainer. Okay, let's dive into this. Today, we're going to put on our virtual hard hats and look at the world a little bit differently. We're going to look at an incredibly common material, but through the precise, analytical lens of a metallurgical engineering student. We are going to systematically break down the hidden chemistry, the generation principles, and the absolute engineering marvel that is iron.
So what is actually inside a standard steel bolt? To the untrained eye, it's kind of just a dull piece of gray metal, right? Just a simple fastener holding our world together. But if we zoom in and look at it through our metallurgical engineering lens, it's an incredibly complex chemical ecosystem. It is a carefully orchestrated balance of very specific elements.
If we look at the atomic makeup of that bolt, right beyond the base iron itself, we find these 5 fundamental elements mixing it up with the metal. We got carbon, silicon, manganese, phosphorus, and sulfur. Now, I really want you to frame these not as random impurities, but as the essential structural ingredients that we're going to reverse engineer today. Understanding how these 5 elements get into the iron and how they behave once they're actually in there is the absolute foundation of metallurgical engineering. Here's our engineering blueprint for today. First, an intro to the 5 elements, then overcoming temperature limits, checking pig iron element ratios, analyzing a fatal weakness caused by sulfur, deploying manganese special forces, and finally, zooming back out to the microscopic bolt world. Section 1. Intro to the 5 elements. Analyzing the raw materials of iron production. The generation principle of iron starts in a massive blast furnace, and it requires 2 absolutely primary raw materials to be loaded right into the top. First, we have iron ore, which comes in the form of fines, or small chunks, mined straight from the earth. But here's the thing, the iron ore can't do the job alone. It has to be combined with a crucial additive called coke, which is essentially a processed coal product made almost entirely of carbon.
Section 2. Overcoming temperature limits. The thermodynamic hurdle of melting iron.
1,539 degrees Celsius. That is the stubborn, fiercely high melting point of pure iron. Now, in the blast furnace, engineers pump in a hot blast of air from the bottom. But this hot blast, it only reaches about 1,200 degrees Celsius. And well, 1,200 degrees simply isn't hot enough to melt iron that demands 1,539 degrees. Let's walk through the brilliant thermodynamic steps of how they solve this. First, the hot blast is introduced at 1,200 degrees Celsius. Next, remember that coke we added? Because coke is mostly carbon, it violently reacts with the oxygen in that hot air blast. This chemical reaction creates CO2, and far more importantly, it generates massive amounts of its own heat. It pushes the internal temperature of the furnace all the way up to 1,600 degrees Celsius. By basically weaponizing the chemical reaction of coke, the pure iron finally and successfully melts at 1,539 degrees.
Section 3. Pig iron element ratios. The birth and composition of pig iron.
Inside this newly formed liquid, which engineers call pig iron, we find highly specific analytical ratios of our 5 distinct elements. We're looking at roughly 4% carbon, about 1.5% silica, 0.5% of manganese, and trace amounts less than 0.05% for both phosphorus and sulfur. The remaining 93 to 94% is, of course, your base iron.
What's truly fascinating here is the origin source for each element. Carbon comes from the coke. Silicon, phosphorus, and sulfur, those are all natural impurities that just sort of hitch a ride in with the raw iron ore. But manganese? Manganese is intentionally added to the mix. It doesn't just happen to be there. Engineers actively put it in.
Section 4. Fatal weakness. Sulfur. The catastrophic threat of hot shortness. So you're probably asking, why do we intentionally add manganese? Well, because if we leave sulfur unchecked in the iron, it causes a catastrophic structural failure known in the industry as hot shortness. Hot shortness is exactly what it sounds like, a fatal physical flaw where high-temperature brittleness causes the solid metal to literally crack, tear, and break when it's being hot-worked or stressed. The chemistry here is wild. When iron and sulfur are heated together without any intervention, they naturally bond to form a compound called iron sulfide. Let's compare these crucial melting points. Pure iron melts safely and strongly at 1,539 degrees Celsius, but iron sulfide it is incredibly weak, melting at just 1,200 degrees. That means that inside a hot, solid piece of steel, microscopic pockets of iron sulfide will melt and turn to liquid way before the rest of the iron does. These tiny liquid pockets create massive weak points, literally causing the metal to tear itself apart under industrial heat. Section 5. Manganese Special Forces. Subduing sulfur at the atomic level.
So how do we stop this microscopic structural failure? There's this great saying in metallurgy for this exact process. Manganese acts as a special forces unit, capturing the sulfur before it can combine with the iron. It is literally a microscopic battlefield. When manganese is dropped into the molten iron mix, it has a much higher chemical affinity for sulfur than iron does. The manganese actively hunts down the sulfur atoms and binds with them first, completely preventing the creation of that weak iron sulfide.
By intercepting the threat, the manganese and sulfur form a brand new compound, manganese sulfide. While the dreaded iron sulfide melts at a weak 1200 degrees and causes cracks, this new manganese sulfide stays completely solid and stable all the way up to 1600 degrees Celsius. It is a total game changer. The structural integrity of the iron is fully protected because the weak points have essentially been engineered out of existence.
To guarantee this chemical stability, metallurgical engineers use exact tactical percentages. A standard addition is about 0.5% manganese, but for extra protection in what's known as low manganese steel, they can bump that up to 1.2%. No matter the exact ratio, though, the primary goal remains exactly the same: the total and absolute prevention of hot shortness.
Section 6. Microscopic Bolt World. Zooming back out to the final product. The macro strength of a simple, everyday steel bolt is entirely dependent on the microscopic chemical battle we just explored. It isn't just iron. A strong steel bolt is a perfectly engineered, carefully balanced matrix of iron, carbon, silicon, manganese, phosphorus, and sulfur. Without the coke raising the temperature, we'd have no iron. Without the manganese hunting down the sulfur, the bolt would literally crumble under high heat and stress.
Which leaves us with a final, kind of mind-blowing question. What other everyday materials are hiding a microscopic battlefield of engineered chemical solutions? The next time you see a skyscraper, a bridge, or honestly even just a bolt on your desk, remember the metallurgical engineering that went into it. Remember the 5 elements, the thermodynamic hurdles, and those manganese special forces keeping it all together. It makes you look at the physical world in a whole new way, doesn't it? Thank you for joining me for this explainer, and keep questioning what everything is made of.